Hello, this is Dr. Brown. Today we're going to start getting into trigonometry in section 7.1, and we're going to begin to talk about angles and their measure. Some of the items we're going to be looking at are we're going to look first at converting between decimals and degrees, minutes, and second measure for angles. You generally think of angles measured in degrees, but then we're going to talk about minutes, which is 1/60th of a degree, and seconds, which is a second is 1/60th of a minute. We're also going to look at finding the length of the arc of a circle. And then we're going to talk about a new measure of angle, and that would be looking at angles measured in radians. And we're going to look at how to convert from degrees to radians and from radians to degrees. Then we're going to look at how to calculate the area of a sector of a circle, and then look at the linear speed of an object traveling in a circular motion. To start off with some terminology, we have a line segment here, or we might even call this a half a line, because we start at a place called the vertex and go out from the vertex in a certain direction, and then put an arrowhead on the end of the line. Now, some more terminology. We have an angle here. We have a ray, which we call the initial side of the angle. And then we go a certain number of degrees to the terminal side of the angle, and we call this angle alpha. Alpha is just a symbol for an angle. We can also use a symbol beta, and in this particular case we could go from an initial side, and instead of going counterclockwise, we can go clockwise and go a certain number of degrees and end at the terminal side. We could also have a case in which we, say, go counterclockwise, have an initial side, go around 360 degrees, and keep on going for, say, perhaps 30 degrees, and this particular angle we call gamma. Also, I'd like to point out that often the symbol theta is used for an angle in lots of cases. Now, looking at our XY plane, let's have some more terminology. We call this looking at the standard position of an angle. We would start at the initial side and go counterclockwise, an angle theta. And here, if we're going counterclockwise, theta is positive. So you need to get a hold and understand the terminology. If we are going this way, positive angle. If we're going clockwise, it's a negative angle. So in this case, if we have a vertex on the initial side and go clockwise, the angle is said to be negative. So for instance, this angle would be 90 degrees plus about 30 degrees, about 120 degrees, and it would be negative 120 degrees. This angle here, which is a positive angle, would be about 90 plus 30, about 120 positive degrees. More terminology. When we look at the XY plane and the XY axis, we talk about quadrants, and we start off with X and Y both positive, and we call that quadrant one, going around counterclockwise. We're in quadrant 2, then quadrant 3, and then quadrant 4. In this particular case, the angle, we say, lies in quadrant 2. In this case, the angle is a negative angle, and it lies in quadrant 4. In this particular case, the angle is positive, and it is about 270 degrees, and it's called a quadrantal angle, and that just basically means the terminal side either ends up on the X or Y axis. Look at several other cases. Let's start at the terminal side and end up on the same side, and we have traced basically a circle, one revolution, which you know is 360 degrees. If in this particular case you can see that we've gone 90 degrees and it's a right angle, that's 1/4 of a revolution. Counterclockwise, it's 90 degrees. This particular case, if we go 180 degrees, we start on the initial side and go 180 degrees to the terminal side, and we say the angle is 180 degrees. Now let's take time to draw some angles. "45 degrees looks like this. A minus 90 degree angle, you would start on the initial side and go minus 90 degrees. So this would be minus 90 degrees. 225 degrees. So here we're going to go counterclockwise. 225 degrees. We'd need to go 180 plus another 45. And this would be plus 225 degrees. Notice it's 180 degrees, and to get to 225 we need to add 45 more, and there we have 225 degrees. Now to do 405 degrees we need to go 360 In other words, go all the way around and go 45, let's see, and go 45 degrees more. So go 360 and go 45 degrees more. And so this angle would be 405 degrees. So on the next page, you see a prettier drawing of what we just did. 45 degrees, minus 90 degrees, 225 degrees, and then go 405 degrees, which would be 360 plus 45. Now, we're going to learn how to convert between a decimal and degree in minutes, seconds, as measured for various angles. Here's the definition of 1 counter clockwise rotation equals 360 degrees. I'm sure you already knew this. 1 degree is 60 minutes, and 1 second is 1 minute is 60 seconds. So let's go ahead. I'll cut that out. Clean this up a little bit. Okay. Begin 1 counterclockwise revolution is 360 degrees. 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. So this means minutes, and double dash means seconds. Okay, we're going to do an example converting from degree, minutes, seconds from form and the decimal form. So we're going to show how to go from degrees, minute, and second to decimal form, and from decimal form to degrees, minute, and seconds. So we'll first of all going to take an angle that's 50 degrees, 6 minutes, and 21 seconds to a decimal, and then round to the nearest 4 places. And then secondly, we're going to convert from 21.256 degrees to the degree, minute, and second notation, and then round to the nearest second. So let's first do 50 degrees, 6 minutes, and 21 seconds. Because 1 minute is equal 1/60th of a degree, and 1 second is equal 1/60th of a minute, then 1 second is equal to 1 over 360 degrees. So here's how we would do the conversion. 50 degrees, 6 minutes, and 21 seconds is 50 degrees, 6 minutes, and 21 seconds. So we write down 50 plus 6 times 1/60th to convert the minutes to degrees, and then add the 21 seconds and multiply by 1 over 360. And so when you add all this up, you get 50 degrees plus 0.1 multiplying 21 times 1/60th times 1/60th, we get 0.0058 degrees. Adding all this up, we get 50.1058 degrees. Now, converting from 21.256 degrees to minutes and seconds, we first write that 21.256 is 21 plus 0.256 degrees. And this becomes 21 degrees plus 0.256 times 60 minutes, because a degree is equal to 60 minutes. So now we have converted to degrees and a number of minutes. And now we can break this up into 21 plus 15 plus 0.36 minutes. And 0.36 minutes is 0.36 times 60 degrees, gives us 21.6 seconds. Because if that's in minutes and we want to go to seconds, we multiply by 60. So adding all of these up, we get 21 degrees, 15 minutes, and rounding to 21.6 seconds off to the nearest second would be 22 seconds. Now, we're going to identify a new way of measuring angles, and this is to understand the measure of an angle in radians. Now, to define what a radian is an angle in which you have a sector of a circle, radius of r, and the angle is such that the arc that it intercepts is also the radius of the circle. And so this is 1 radian. Now, by the same token, you could have, say, a circle of radius 1, and you have an arc here of 1. You then could extend the circle to have a radius of 3, And that same angle would have an arc length of 3. So either way you look at it, this angle is 1 radian. So to get a feel for radians, notice that in this example, where the arc length is r and the radius of the circle is r, that this theta 1 is equal to 1 radian. Well, suppose we draw a 90-degree angle, theta 2. Theta 2 equals what in radians? Well, notice that the circumference of the circle is equal to 2 pi r. So this arc length for 90 degrees would be 1/4 of the circumference of the circle. So this S is going to be 2 pi r divided by 4. So this arc length is going to be pi over 2 times r. So theta 2, the angle, is going to be pi over 2 times r divided by r times 1 radian. Notice that the angle here is going to be directly proportional to the arc length. So if this arc length is pi over 2 times r, and this arc length is r, then the ratio of the two would be pi over 2 r divided by r times 1. And so this is pi over 2. The r's cancel, pi over 2 radians. So now, just briefly, a quarter of a circle is pi over 2 radians. A half a circle, which is 180 degrees, would be twice that, or pi radians. 3/4 of a circle would be 3 pi over 2 radians. Now, how can we find the length of an arc of a circle? Notice that in this particular drawing, we have two arc lengths, capital S and S1, and the corresponding angles are theta and theta 1. Suppose theta 1 was a whole circle, so it would be 2 pi. That means S1 would be 2 pi times r. And because the ratio of the angles is directly proportional to the ratio of the arc lengths, we would now have theta over theta 1, which is 2 pi, equal S, which is the arc length of corresponding to theta, divided by S1. S1 would be 2 pi r. And looking at this particular equation, we can multiply both sides by 2 pi, and the 2 pi's cancel, and we get that theta is equal to S over R. And now cross multiplying, we get S is equal to R theta. So now we have a really important equation saying that the arc length of a sector of a circle is equal to the radius of the circle times the angle, and the angle theta must be in radians. So here we have a formula or a theorem for a circle of radius r, a central angle theta of theta radians, subtends an arc whose length is S equal R times theta. So S is equal to R times theta, where theta must be in radians, not degrees. So if you're given an angle in degrees, you need to convert it to radians. Okay, example, find the length of the arc of a circle of radius 2. With an angle of 0.25 radians. So we want to find this S with a radius of 2. And the answer is on the next page. It's going to be S equal R times theta. The radius is 2. The angle is 0.25 radians. And the answer is 0.5 meters. So that says if you have a radius of 2 and an angle that's 0.25 radians, this length is a half a meter. We'll be using this a lot. Now, we need to understand how to convert from degrees to radians and from radians to degrees. We know that 360 degrees is 2 pi radians. And we know that 180 degrees would then be pi radians. So noting there are pi radians at 180 degrees, 180 degrees in pi radians, we can convert either way using this information. So in a full circle, 1 revolution is 2 pi radians. That's 360, as we said. 1 revolution is 2 pi. A half a revolution is pi radians. So 1 degree is equal to pi over 180 radians, and 1 radian is equal to 180 divided by pi degrees. On the next page, I will show you how to do conversion. We want to convert 60 degrees to radians, 150 degrees to radians, minus 45, 90, and 107. Now, we already know 90 because we already did that, but looking at the conversion scheme, we'll show that that will be pi over 2. Okay, so let's go. 60 degrees, I would write down 60 degrees and then write, multiply it times pi radians per 180 degrees. So write degrees down here. Notice the degrees cancel. 60 goes into 183 times, so we end up with pi over 3 radians. 150 degrees is 150 degrees times pi radians divided by 180 degrees. We know we're right because we're getting the degrees to cancel, and we're going to end up with 150 over 180, which is 15 over 18. Divide both top and bottom by 3, and we get 5, 6 pi radians. Minus 45 degrees is minus 45 times pi radians per 180 degrees. So we get minus 45 over 180 radians. And that equals minus pi over 4. 45 and 180 is 4. 90 degrees, we already know it's going to be pi over 2 degrees, but let's show how we get it. 90 degrees times pi radians per 180 degrees. 90 goes in 182 times, and we get pi over 2 radians. Now, 107 degrees is converted to 107 degrees times pi radians per 180 degrees. The degrees cancel, and multiply 1.07 on your calculator times pi, which is 3.14159, etc. Do that and you get to the nearest thousandths 1.868 radians. Now, we want to show how to go in the other direction. Pi over 6 radians, 3 pi over 2 radians, minus 3 pi over 4 radians, 7 pi over 3 radians, and 3 radians. We want to convert these to degrees. So here we go. Pi over 6 radians is equal to pi over 6 radians times 180 degrees per radians. Notice our radians cancel. 6 goes in 180 30 times, 30, and 180 degrees per pi radians. The pi's cancel, and we get 30 degrees. Converting 3 pi over 2 radians to degrees, we get 3 pi over 2 radians times 180 degrees per pi radians. The pi's cancel. 2 goes into 180 90 times, and 3 times 90 is 270, so we get 270 degrees. Let me erase a little bit of this to give some room. Converting minus 3 pi over 4 radians to degrees, we get minus 3 pi over 4 radians times 180 degrees per pi radians. Pi's cancel. 4 goes into 180 45 times. So minus 3 times 45 is 135 degrees. 7 pi over 3 radians is 7 pi over 3 radians times 180 degrees per radian, per pi radians. Radians cancel, pi's cancel. 3 goes in 180 60 times. So we get 420 degrees for 7 pi over 3 radians. And finally, 3 radians is equal to 3 radians times 180 degrees divided by pi radians. And multiplying 3 times 180 divided by pi gives you approximately 171.89 degrees. Now here's just a table of commonly encountered angles. Some of these we've already done. As you see, 180 degrees is pi, 90 degrees is pi over 2, 150 degrees is pi over 6, and you see some equivalent ones in degrees and radians. So as you do more and more of these problems, you'll begin to realize things like 90 degrees, pi over 2, 45 degrees, pi over 4, 30 degrees, pi over 6, etc., etc., etc. 60 degrees is pi over 3. So the more trig problems we work, the more you'll understand the conversion between these degrees, the angles in radians and angles in degrees. Now, this is just an example of a picture of the globe, which the Earth is pretty much almost perfectly round and has a radius of about 4,000 miles. And I'm sure you're familiar with latitude and longitude of points on the Earth. This is just an example of figuring out how far 2 points on the Earth are from each other along the surface of the Earth. If they are at roughly the same longitude, if they're, in other words, on the same longitude line, and say Sioux Falls was 43 degrees 33 minutes, and Dallas was 32 degrees 46 minutes, we would figure out that Sioux Falls is 43 degrees 33 minutes, and we're going to subtract the two to figure out how many degrees there are between Sioux Falls and Dallas. So to do the subtraction, we would have to write the 43 as 42 degrees and 60 plus 33. which will be 93 minutes. Now we want to subtract 32 degrees and 46 minutes from that. And so we can see that the difference subtracting is 10 degrees. And let's see, subtract 46 from 93. We get 47 minutes. So 10 degrees, 47 minutes. And that would be 10 and 47 over 60th degrees. And you would convert this to radians and then use the equation S equal R theta. The radius is 4,000 miles, and the angle is 10 degrees, 10 and 47/60th of a degree. Convert that to radians, and you would have the distance between them. We'll have some of these problems in your homework and probably on the next test. So I'd like for everybody to make this calculation, converting this to radians, and tell me how far Sioux Falls and Dallas are from one another. And I'll just ask you all to email me how much it is, and I'll tell you what the answer is. Now, how do you find the area of a sector of a circle? If you have a sector of a circle that has an angle theta, and you want to find its area, and its radius is r, it's pretty obvious that the area of the circle is pi r squared. And the angle theta is 2 pi. So finding the area A, we would just take theta divided by the angle of a full circle, which is 2 pi, times pi r squared. Okay. And canceling out the pi, we get 1/2 r squared theta. So we have now an equation for the area of a sector of a circle is equal to 1/2 r squared theta. So now find the area of a sector of a circle of radius 2 formed by an angle of 30 degrees and round the answer to 2 decimal points. We're going to use the equation A equal 1/2 r squared theta, and go ahead and we'll plug this in on the next page, and we get 1/2 r squared, which is 2 squared, times the angle, which is pi over 6, and this turns out to be pi over 3, which is about 1.05 square feet. And the last topic we're going to talk about in this lesson is how to find the linear speed of an object traveling in a circular motion. If an object moves on a circle of radius r at a constant speed, or suppose it does move on a circle of radius r at a constant speed, if s is a distance traveled in time t on a circle, then the linear speed is just the velocity equal the distance it travels divided by the time. This equation is really, this distance s, you probably is equal to the rate times the time. In this case, it's the velocity times the time. So the distance travel is the velocity times the time, and the velocity is the distance divided by the time. So here we are, circle of radius r, in time t, an object going round and around travels a distance of s, which represents an angle of theta, and r is a radius. We now define what we call the angular speed, which is equal to the angle that the object travels through divided by the time, and this is called omega. So we have omega is equal to theta over t. And the velocity, the linear velocity, would be r times omega, where r is a radius, and omega is measured in radians per unit time. So now we've got a child spinning a rock at the end of a 2-foot rope. That means r is 2, at the rate of 180 revolutions per minute. Find the linear speed of the rock when he lets go of it and it's released. Notice when he lets go of it, the object will begin to go in a linear direction at the speed at which he releases it. So let's calculate this. First of all, the angular speed of the rock is omega is 180 revolutions per minute, which is, converting it to radians per revolution, would be 2 pi. If each revolution is 2 pi radians, he's doing 180 revolutions per minute. Its angular speed is going to be 360 pi radians per minute. Now the linear speed then of the rock is going to be, the velocity is equal r times omega, which is 2 feet, times the 360 pi radians per minute. That equals 720 pi feet per minute. 720 pi with pi about 3.14 is equal to 2262 feet per minute. The linear speed of the rock when it's released is 22.62 feet per minute, which is about 25.7 miles per hour. And that is the lesson for today.